Yeah, now we are online, Professor. We may begin the session.
Yeah. Okay. So we have, I hope some of you were there. All of you were there in the last class, and we were discussing some of the basics, and then we were trying to understand a simple experiment. So let me just ask you if you have some questions. Of course, I asked you people to just message some of the questions in the Telegram group so that I thought we can save some time. But since many of you, only some 20 to 30 people are here, maybe if you have some questions from last class, you can ask. So any you don't have to repeat if you have written in the Telegram group, but if you have not written and you have some question, you can ask.
Excuse me, sir.
Yeah.
Sir, in the previous class, you have talked about a wave packet. So can you please explain, please, why we are always scared about wave packets rather than a single wave, even though associated with a single particle or like a photon?
Okay. So that is a nice question. So we will we'll have to worry about why wave packet and why not a wave. Okay. Any other? I think someone, Sarandas, if I remember correctly, has written a mail or a message to me that you talked about wave particle duality, but what is the connection of wave particle duality to the experiment that you discussed? I think that was one question. Which is that correct, Sarandas?
Yes, sir. Yes, sir.
Okay.
I have I sent it the message in Telegram, sir.
Okay, in Telegram. Yeah. Okay. Oh, you didn't send it in the group, but I think you sent it to me. That's how.
Yes, sir, in private mode.
Okay. So I am just recalling that question also here because it's all, even such questions are important. So that's why I'm saying whatever question you have, you can ask.
Sir, I will post that question in the chat box, sir. Here.
Anyway, I have. You can post it, no problem.
Professor Sarandas, I think, has raised some question. If you permit, you can straight away ask the question.
No. That's what he has already written to me.
Okay.
So the same question he has put it in the chat box.
Okay, Professor.
That is what I already talked about that question just now. Okay. So anything else?
Sir.
Okay. Yeah.
So what will happen when we put the polarizers in opposite angles, sir? In previous class, in the middle of the photon source, photon probability, sir.
Okay. So you are saying one should be the polarization axis should be perpendicular to each other.
No, sir. No, sir. You show us a diagram, sir.
Correct. So I think we have the following diagram here. This is the last class. So I think this is what
yes,
I
sir,
have,
yes.
right? Okay.
Yes,
what is the question?
what will happen when we put the polarizers in opposite direction?
That's what this P2 should, you want to put this P2 to be in this way, right? In this
Yes, sir. Yes,
particular
sir.
way, right? Yeah,
Yes,
so
sir.
then nothing comes out because this direction is perpendicular to this, right?
Yes, sir.
So,
Sir, but some of the photons will cross in the center, sir. What about it, sir?
some of the photons will cross. Okay. Anyway,
Cross
let
at the
me.
center of.
Okay, so let me briefly discuss this experiment once again because George also has mentioned the importance of this experiment. So let me just mention this experiment briefly so that it might recall. So let's say I have a source. Okay. So this source is emitting polarized photons. Okay, so each polarized photon I want to represent like this. So this is the polarization direction. Okay, so now let us say that I have a polarizer whose axis of polarization is like this. Then you ask a question, what happens? Okay, so what happens? Muthuchami, can you tell me now what happens?
It will come out, sir, with
It
no
will come
change.
out, no change. So all of them will come out. Okay, this is known for us. So what do we say? So let us say we talked about two properties, right? Transmission and absorption. So what can we say about probability of transmission here? Probability of transmission is equal to 1. Probability of absorption is equal to 0. Is that correct? It definitely comes out means what? Probability of transmission is 1. Probability of absorption is 0. Correct? Now,
Yes,
on the
sir.
other hand, if I put a polarizer where the axis of polarization is like this, then what happens? What happens after this?
So no
No
transmission.
sources are coming out.
Nothing will come out, right? What does that mean? Probability of transmission is 0. Probability of absorption is 1. Correct? Everything will be absorbed. Nothing comes out. This is clear, right?
Yes, sir.
Yes,
Okay.
sir.
Okay. So now what we are going to do is that we are going to take a source of photons which are polarized in this particular way, and then insert a put a polarizer whose axis is like this. It is not along this or perpendicular to this, but it makes an angle theta. So let's say this angle is theta. Then what can you say about this, about the photons?
So partially will come out and partially will be absorbed.
So what do we mean by partially coming out?
Sir, here the probability, transmission probability will be proportional to cos square theta. Sir, I have a question. How these single photon experiments are carried out? Means how do we, what can be the source? Only single photon will come out of it.
Yes, right now we have a very good sources which
Am I
give you
audible,
single
sir?
photon. Yeah, you are audible. I understood your question. So what I'm saying is presently there are sources which will give rise to single photon. Okay, now how do we know that single photon is coming out is a good question. But quantum mechanics tells us that when you let's say you have a hydrogen atom, you take electron from n is equal to 1 level to n is equal to 2 level, and when it comes back, you will get a photon of a particular frequency, right? You will get one photon. So like that, you can use quantum mechanical quantum mechanics to actually engineer sources which will give you photon by photon. Okay, in the olden days, people did experiments of single photon experiments by actually reducing the intensity of the light that is coming from these sources, sometimes by putting some kind of filters and things like that. So lower intensity means the intensity is basically the number of photons. So lower intensity means less number of photons. So I think in 1908 or so, Taylor did an experiment
So
where.
basically the time gap is.
Say that again.
Sir, I'm asking. So the control means the time is controlled. One photon will come, then after some time, one more photon will come.
So
like that.
now you can also, I mean, present day technology will allow you to engineer this time. So you can also do an experiment where one photon comes out and it passes through this polarizer, and only then the second photon comes out. So it is possible to do an experiment like that. Okay, so it is possible to, we have sources of that type where we can actually control the time of emission of these photons.
Like these are these femtosecond lasers, those things, or like this pulsed laser, or
no, pulse laser is different. See, laser, when you say, it is a classical source only. Whether it is a continuous laser or pulsed laser, laser is a classical source. It gives you only electromagnetic waves. Now, femtosecond pulse is like a wave packet that we are talking about. It's a wave packet of electromagnetic waves. That's all. Correct? So it is not like that. These sources are basically like, for example, there is something called a calcium atom. An excitation of calcium atom will undergo a de-excitation, giving rise to a photon of a particular energy. So that will give only one photon, because you are giving only energy for one excitation. When it gets de-excited, it will give one photon. Now you can excite this atom at some interval, right? You can always excite. Now I will excite it, I will get a photon. Then I will excite it after, let's say, 2 seconds only. Then I will get another photon only after 2 seconds. Because once excitation takes place, de-excitation is almost instantaneous, because the spontaneous emission rates are very high, and the lifetime of the electron in the higher excited state is very, very low. So you can always engineer the photon emission in that fashion. Okay. But anyway, at this point, I don't want to go into technical details of how these photons are produced. But please believe me that it is now possible to produce such photons. So I am trying to do this, discuss this experiment in that background, that we can actually do this experiment. So now the question, yeah.
Sir, you said this photons we can produce by excitation of atomic levels, right? Because they are sharp.
Yeah.
But sir, every these atomic energy levels, they are also have a finite width, right?
Correct. So, correct. So they also have a finite width. So the lifetime is. So you can always think in terms of certain levels which are long lived. Okay, and hence their lifetime will be very small. Okay, so that is why every atom, see, you can excite any atom, but you will not be able to use them as sources. So there will be other details that you have to work out, which are more long-lived excitations, and then so that is important. Otherwise, there is going to be some spread. But then one has to look at how much spread is compared to the frequency and things like that.
Yes, sir.
Okay, so it's a very detailed detailed field. Producing them is not very easy, I am saying, but since it can be produced, I am going to simply say that there is a source, but you have to write a textbook to understand how this source gives the single photons.
Yes, sir.
Okay,
Sir, one more doubt.
Yeah.
Sir, in this experiment, when the axis of that polarizer is crossed, when the photon pass, either it will come out or it will not come out because of some interaction with that instrument. Now, sir, do we have any development in understanding how the photon interacts with this apparatus, or do we have any control upon it?
No, as of now, there is no control.
Yes, sir.
And as of now, we don't have a complete understanding also how it interacts with this polarizer.
Yes. Yes, sir.
Okay. And somehow this is a very tough problem, and we don't have much. Some speculations are there and some guesses are there, but nothing is kind of a settled. It's not a settled issue. Okay. So what happens there is still kind of a. It's like my guess is as good as your guess at this moment.
Okay, sir. Thank you.
Okay. Yeah. So now the question that we have to ask is that if you consider a single photon, okay, a single photon, so I called this one as P1 in my last class. So let me call it as, so single photon crossing P1. So the question is, suppose if you ask what happens? Okay, so the honest answer to this question, honest answer is we don't know. Okay, now we would like to get some understanding. So let us do this experiment. Let's say one photon comes out. So let us say photon number 1, it is coming out. Photon number 2 is not coming out. Photon number 3 is coming out, and so on. Okay, so do this experiment. With n photons, one at a time. Okay, so if you do this experiment with n photons, one at a time, each photon is either coming out or not coming out. Okay, one of these two things is happening. So each photon either comes out or does not come out. So this is our experimental observation. So when we do an experiment, this is what it looks like. Then when you observe n photons, among n photons, n cos square theta photons come out on an average. Exactly this many will come out, I will not be able to say. On an average, n cos square theta come out. Now this is our observation of this experiment. Then we know that classically a beam of intensity I, when passes through P1, we get a beam of intensity I cos square theta. We get intensity I cos square theta after P1. Okay, and this is what we call as Malus law. Now, we would like to say that there should be a correspondence between this result and this result, because large number of photons should give us the classical behavior. Okay, so these things should be related. There is no doubt about that. Okay, that is the famous correspondence what Bohr talked about. So now we can ask a question. From this correspondence, what can we say about a single photon? Okay, so that is the question that we have to answer. Okay, a single photon. So this question is very important. What happens? Honestly, the answer is we don't know. Okay, now we ask this question that we don't know what is going to happen. Okay, exactly what is going to happen we don't know, but we can ask a question for a single photon crossing P1, what are the possible things that can happen? This is not a question like previous question. Okay, so I will simply call them from now onwards as possibilities. We don't know what will happen, but we can always ask, what are possibilities? Like, for example, toss a coin, and you ask what will be the outcome. Ask the question. Honestly, the answer is we don't know. Okay, but you can ask what are possible outcomes. Okay, so this is a good question, and this has an answer, head or tail. These are the two possible outcomes.
So basically the sample space, sir.
Hmm?
The sample space.
Possibilities are basically the sample space in the language of probability. So we can ask what are the possible things that can happen. So the possibilities. Now, from our analysis of this experiment, we know what are the possibilities. Okay, so the possibilities essentially here are, it can come out or it can get absorbed, transmitted or absorbed. These are the two possibilities. How did we know? We know this by just looking at this experiment. Okay, now looking at this experiment, we know that these are two possibilities. Now, not only that we know these are two possibilities, there are two possibilities, and we will not be able to tell what happens for a given photon. These two things together, what happens is that for every photon, T or A result randomly. Why we say randomly? Because we are not able to say beforehand. Okay, why? Since we cannot predict the result.
So the outcome is a random variable. So here, can we say that?
Yeah, outcome is basically one of these two randomly.
I'm saying the random variable. Outcome is a random variable.
No, random variable is just see, when you say you have a sample space, a head tail like that. Now, when head comes, you assign some variable. T comes, you assign some variable. Then it becomes a random variable.
No, like X
At
is
this
a
moment,
random variable. Capital X is a random variable. Now X can take values head or tail.
no. See, random variable means it is always okay. One can. This is just a kind of a small language issue only. If you want, you can call this as a random variable. There's no problem.
Okay, sir.
Okay, so essentially, what I'm trying to say is, we cannot say what is going to be the outcome or what is going to be the result beforehand. So no prediction is possible. Because we are not able to predict, we will not be able to say what will happen to a given photon honestly. But we can only say that one of these two things happen, and these two things also we will not know what will happen. So the sum total of what can happen we know, but we don't know for a given photon what happens. So whenever we have this kind of a situation, okay, so that means, so random, whenever randomness is there, then we have to estimate this randomness. Okay, so quantification of chance, which essentially is randomness. The quantification of chance is done by assigning probabilities to different possibilities.
So
okay.
Excuse me, sir.
Yeah.
So is it mean that before performing the experiment, we cannot define the actual state of the system? Like we cannot know about the probability amplitudes, right? Before without performing the experiment.
As of now, I want you to understand like that. Okay, but that's not the final story. But let me just, at this moment, let's say what you are saying is the situation. Okay. So in this example, I want you to understand it like that. So we are going to actually develop these notions a little further. Then you will understand it clearly. So now we do. So we have now said that since there is a randomness, I have to talk about probabilities. Now to define these probabilities, we have to make this correspondence. What is the correspondence? We know that if it is a classical case, it is I cos square theta. Now what is observed in this experiment is n cos square theta. Okay, so this is classical result, and this is the result from our experiment. Now there should be a correspondence between these two. Now if there is a correspondence between these two, and then there is a probability that is required, so these n square cos square theta are transmitted. Okay, that means probability of transmission for a given photon has to be equal to cos square theta. Okay, for a given photon. Okay, so this is what I am going to assign. Because if I do like that, so every photon has got a probability cos square theta. Then how many number of photons will come out if n number of photons are used in the experiment will be n cos square theta. Okay. So this n cos square theta is equal to n into probability of transmission. Okay. And probability of transmission plus probability of absorption has to be equal to 1. Why? Because there are only two possibilities. So total probability has to be equal to 1. This will tell you probability of absorption has to be equal to 1 minus cos square theta, which is equal to sin square theta. So right now we have assigned these probabilities. Okay. Now you put theta equal to 0, you will get the first case where the axis is along the same direction. P of t is 1 and P of a is 0. If you take theta equal to pi by 2, it comes to the second case where you have put the polarizer with a perpendicular axis, then P of t is 0 and P of a is equal to 1. So whatever observations that we have in this experiment are perfectly agreed if we assign these probabilities. Okay. Now, so far so good. So any question at this point, up to this point? How we are assigning the probability, is that clear?
Yes, sir.
Yes, sir.
Okay. Very
But sir, from the last class, I have a doubt regarding this. Like,
good.
sir, like you mentioned that we don't know the outcome, like which is true, correct? But that reflects our ignorance. But in quantum mechanics, the uncertainty is fundamental. No, sir.
Yeah. So we'll come back to that. So at this point, I am just saying that, okay, we have assigned these probabilities. Okay. Up to this, what is the input that we have? We are doing this experiment. So what is our experimental result? Our experimental result is that we don't know what is going to be the outcome. And we observe that there are two outcomes, either transmission or absorption. And these two together tells you that for every photon, transmission or absorption happens randomly. If you use large number of photons, n cos square theta of them will come out. That means so many will be transmitted. Since they happen randomly, the randomness has to be quantified by assigning probabilities. And since n cos square theta, if you write it as n into p of t, then p of t can be written as cos square theta. And since p of t plus p of a is equal to 1, p of a will be sin square theta. So this much is for assigning the probabilities. Okay. Now we will ask the following question. We have assigned the probabilities. Okay. So far, the situation is very nice. Now what we will do is we will continue this experiment. So let's say that I have a source. And then these photons are coming this direction. Now I have put a polarizer, then some photons are coming and some photons are not coming. That is fine. So now, suppose I have n cos square theta of them have come here. So totally n of them are coming from here, n cos square theta are coming here. Now suppose if I put another polarizer P2, so let's say this is what I called as P1 and this is what I called as P2. Now, if we do this experiment, how many number of photons will come out of this? The axis is parallel to this. Okay, so axis of P1 and P2 are parallel. Okay, so I think axis of P1 and P2 are parallel. Now, experiment tells you that here also it is n cos square theta. So what does that mean? So every photon that got transmitted, at P1 also got transmitted at P2. So what does that mean? So from here to here, when you are crossing this one, probability of transmission is cos square theta, and probability of absorption is sin square theta. Okay, so what can we say about probabilities at this point?
Probability of transmission is 1.
Probability of transmission is 1, and probability of absorption is 0. What does that mean? When will this happen?
Like absolute case, deterministic case.
Yeah, so we have seen earlier that when probability of transmission is 1, probability of absorption is 0, means what? The axis of the polarizer and polarization direction of the photon should be same. Correct? Only then P of t equal to 1, P of a equal to 0 is possible. So what does that mean? That tells you that the polarization direction of the photons after this should be like this. It has changed. Okay. So polarization state of a transmitted photon is transmitted photon at P1 has changed from, you can say, this to this. Only then I can understand this result at P2. Only then I can understand this result at P2. Okay. Only then I can understand this result at P2. Yeah. Yeah.
Sir, in first case, means in P1, the photon doesn't know whether it will come out or not, means whether it will transmit or absorb. But in second polarizer, when it comes to second polarizer, it surely knows it will get transmitted. So correct. How beforehand it knows the photon? In one case there is a probability, in other case there is a surety.
Yeah. So like, you can say that here also you talk about probability, but the probabilities are like this. Okay, so theta equal to 0 is because that is how I am drawing this conclusion. Because here probability of t is equal to 1. When will this happen? When the axis of this polarization makes 0 angle with the polarization state, only then it is possible, right? And that is why I am coming to conclusion that the photons before P2 are in this particular state.
Yes.
Okay, I am concluding it because of the probability only. The probability is so skewed here that can happen only if the photon is in this particular state. Correct?
Oh, okay.
So two things is that I am drawing two conclusions. First is that polarization of a transmitted photon is not the same as what it was before. It has changed. And we know what it is also, because in the second polarizer, since it is definitely getting transmitted, it has to make 0 angle with the polarizer. And this angle, these two axes are parallel. So that tells me that when a photon is getting transmitted, its polarization state is parallel to the axis of this polarization state. axis of this axis.
So, sir, this probability is not assigned a priori. It is like assigned after getting the result, right?
Yeah, that's what the other guy also asked. So at this moment, let us keep it that way.
Okay.
So this probability I am only assigning because I am trying to develop all my understanding from this experiment.
Sir, these things happen because of the anisotropy of the polarizer, I think, sir. Because it has a preferred direction in which the photons pass through, and if we rotate it, then there's a direction it doesn't pass through.
Yeah, that is true. But let's not go into details of what is happening inside the polarizer. That mechanism is not of great interest for us at this moment. Okay, because we want to only abstract certain rules based on the gross observations that we make.
Sir, I have a question.
Yeah.
Are you saying that this intensity changes after P1, the intensity changes to n cos square theta? That conclusion we are deriving only after observing the outcome of P2?
No. This conclusion we can derive independent of P2. But when you put P2, the intensity does not change.
Yeah,
it
that's
will be
true.
n cos square theta only.
Yeah, that's true. And then you are concluding that after P1, the polarization must be changing from parallel normal to inclined, right?
Inclined, correct.
So that means you are interpreting what this n cos square theta is. You are interpreting that this n cos square theta must be representing a polarization state inclined to the axis, right?
Yeah, there are two things here. One is what we can observe is only a kind of an average number of photons that are coming out. From that observation, now I am trying to answer certain questions about a single photon. Okay, so that is where there can be a little bit of confusion.
Okay, you are trying to find out, you are trying to think about what is the polarization state of a single photon.
Correct.
Okay.
So from the analysis of results obtained for large number of photons, I am trying to ask what happens to the probability of a single photon, what happens to the state of a single photon. In the previous case also, I have assigned probability of transmission equal to cos square theta, absorption equal to sin square theta for a single photon at P1. Now I am saying, I am going to one step further. What happens to the polarization state of the photon? That I understand by putting another polarizer. It has definitely changed from this vertical up and down to this inclined this thing. Okay, so this conclusion I am drawing after putting my second polarizer here.
Okay.
Can
you, from this probability proportional to, equal to cos square theta result, from that, can we directly conclude that this polarization state is inclined? We cannot do that, right?
No, we cannot do that from that.
Okay.
So unless I put P2, I will not be able to get that result, right?
Okay, correct.
Yeah. Okay, so now, so we have concluded the following thing. The state, okay, when I say state, I mean polarization state. The state of transmitted photon is this. Agreed? The state of transmitted photon is this. Okay. Now, you know that not all photons are transmitted. So you can ask a question, what is the state of an absorbed photon? We don't know, we haven't seen it. But we can ask this question. What is the state of what would have been the state of an absorbed photon? We did not notice that one. Okay, what did not come? So can we design some experiment to find out what is the state of an absorbed photon? So any idea? Any of you would suggest me some experiment to find this out?
So we can reason because the polarization, the optic axis of the polarizer is acting as a cross direction to that polarization, plane of polarization. So that should be the perpendicular direction of the transmitted photon. That is for the transmitted photon.
Okay, so that's a good hypothesis. We can reason out like this. But suppose if I want to do an experiment and then find out whether my hypothesis is correct or not, what kind of experiment can we design?
So we can put a polarizer exactly perpendicular to the first one before the P1.
What's your name?
Vishnu, sir.
Great. Very nice advice. So what Vishnu suggested is that, so let us take a source and then we have these photons. And now we have P1 here. So before this P1, let us put some P0, let me call it. Okay. And then you put P1. Okay. So what will be the result after P1?
Nothing will come out.
Nothing will come out, right? So no photon comes out. What does that mean? Again, let's go back to our initial thing. So I'm getting all photons are absorbed. What does that mean?
The polarization axes are perpendicular, parallel. So in this case, are perpendicular.
Perpendicular. So what does that mean? That means the photons after P0 are coming to what? They must be in this direction. Correct? They must be in this direction, perpendicular to this line. Okay. So that fraction, now you can do an experiment and then see that this will be your n sine square theta. This will be your n sine square theta. And from that, you can say that your probability of absorption is equal to sine square theta. Okay, at P1, by the way. And what should be the state? So we asked this one, what is the state of an absorbed photon? Absorbed photon state is the perpendicular to this one. Correct?
So probability of absorption should be 1, no, sir, because like they're crossed.
No, at this point it is n cos square theta. So here probability of absorption is equal to 1.
Yes, yes.
And probability of transmission is equal to 0. Okay.
Yes, okay, sir.
So from here we understand that somehow, so what is the conclusion? The conclusion that we can draw from this analysis, I think it is English, is that this state is a combination. This state is a combination of this and this. Okay, this state is a combination of this and this. That is why when a photon in this particular state goes through a polarizer P1, there is a possibility that it will come out. There is a possibility that it does not come out. Okay. Now, what kind of, so if you have a state like this, now which one will be the situation, or which one of them is going to so that is something which we don't know. So we have no knowledge of this one. But what we know is that the probability of this one is cos square theta and probability of this one is sin square theta. So this is what we are calling as transmitted. This is what we are calling it as absorbed. And what we know is P of t is equal to cos square theta and P of A is equal to sin square theta. Okay. Now from this knowledge, we should write this as a combination of these two things. Okay. So,
sir, the message in the conclusion has some uncertainty, I would say, because you didn't mention convex combination or linear combination.
Yeah, I didn't mention with a purpose. So that is why I suppressed that word.
Yes,
okay,
there is uncertainty in that message.
Correct. That uncertainty is purposefully I have put that uncertainty, and to recognize that uncertainty, of course, you recognized it because you know something. But in general, I'm going to come to that requirement of linear combination. Okay. So now the point is that can we say that this is cos square theta times this plus sin square theta times this? Okay. So one possibility is that can we simply say that this is equal to cos square theta times this plus sin square theta times this? Because this is like probability, right? Cos square theta times this plus sin square theta times this.
The probability amplitude, so like not cos square.
So the question is, can we write like this? Okay, so the point is that so this is where I think quantum mechanics has to be understood carefully. Now the state of a photon so when I write it like this, okay, the state of a photon, when I write it like this is abstract. Okay, this is very abstract notation. Now you can ask a question, what is this mathematically? So what is this mathematically? Okay, what is this mathematically? Now it turns out that we also know from classical polarization that this can be written as a vector. Okay, so for example, you can write this as 1, 0. Okay, in polarization optics, this is called a Jones vector. Okay, so this can be written as a vector. And the other one, this one is 0, 1. Okay, the perpendicular polarization to this one is 0, 1. So like this one can write down vectors. Okay, so you can say this is whatever. So maybe this is called vertical polarization, or this is called horizontal polarization. Okay, so in this fashion, you can say that you have so what is this? What is this one now? What can we write this one?
So using the vertical and horizontal polarization states as a basis, we can write as a linear combination of them.
Okay, so first recognize that polarization states, polarization, or you can say set of all polarization states, okay, are of this type, some A comma B, okay, set of vectors like this, such that A comma B are complex numbers. A comma B are complex numbers, and mod A square plus mod B square is equal to 1. Okay, so this can be, so this is the most general set. Okay, and if you do not know much about linear algebra, then it is difficult to understand. But if you know a little bit of linear algebra, you can immediately recognize that this is a vector space. This is a vector space. Okay, in fact, it's a two-dimensional, because there are two complex numbers required to define a vector. Two-dimensional complex vector space. Okay, now at this moment, I made this remark that you require a complex numbers here, because you know that we, among the polarization states, we don't have vertical horizontal. We also have left circularly polarized state. Okay, so something called left circularly polarized state. Okay, so that can be written as 1 by root 2 times 1 minus I, something like this. And you have right circularly polarized light, which can be written as 1 by root 2 times 1 I, and things like that. So if you want to define a general polarization state, which is not necessarily linear polarization, then you require to have complex numbers. Okay, we require to have complex numbers. Now, the whole point is something like this. So now what I'm trying to tell you is that let's say that I have a, so this experiment, okay, so this experiment I can do it in the following fashion. That is, I have a source. And then I have these photons in this direction. Okay, sorry. So maybe let me just argue it like this. So let's say I have a source, and this source is giving rise to photons in this particular direction. And now I put a polarizer in this direction. Okay, so if this is n, then this is going to be n cos square theta. Or let me be more specific. So let us say if this angle is, let's say, 45. Okay, so let's say this angle is 45 degrees. So then this will be n by 2. Now in another experiment, I have a source, I have same thing, but then I am going to put it like this. So how many so if n of them are coming, how many number will be there here?
So n by 2, sir.
N by 2. Very good. Now let me repeat this experiment with a source that is giving me some circular polarized state. Okay, and then I have a polarizer like this. Okay, so What do you think will be the number here?
So we have to decompose the circularly polarized light into the vertically and horizontally polarized like
Correct.
in that.
So it's not very easy to answer this question. Okay. So now let us look at what is this 45 degree. This 45 degree. So we call this as diagonal polarization. So this diagonal polarization is equal to 1 by root 2 into 1 1, because cos square theta cos theta sin theta like that, no, 1 by root 2 1 1. So this can be written as 1 by root 2 into 1 0 plus 1 by root 2 into 0 1. Correct? Now notice, okay, I think even here you can understand. So let us go back to this. So from here, you understand that, okay, so what I'm trying to do is, I have probability of transmission is equal to cos square theta. Probability of absorption is equal to sin square theta. Okay, so this is our established knowledge. Correct? Probability of transmission is cos square theta. Probability of absorption is sin square theta. So now so we know that the polarization state has to be written as a vector of a vector of two components. So should we write this as cos square theta and sin square theta? Cos square theta and sin square theta. This is a normalized vector, no problem. But then we know that we have some complex numbers, some like 1i. Okay, so in general they are complex numbers, but these are not complex, right? So so you are going to write it. Suppose let's say we write cos theta and sin theta. Okay, let's say cos theta and sin theta. Is this the right way to write? Okay, then cos square theta plus sin square theta is 1. So this is normalized as such. But then also we don't get complex numbers, right? So what we do is that we say that we have cos theta and sin theta into some other complex phase, which we will put there, and then maybe this is a better way to represent. Okay, so this gives you that there is a possibility of complex numbers coming depending on the value that phi takes. Okay, so then you can have complex numbers also. But then what we are going from here is that we are going from cos square theta to cos theta. Okay, so what we have understood here is that, so let me represent this particular polarization state in a fancy notation like this. This can be written as cos theta into this one plus sin theta into this one. Okay, so you know this is called a Dirac notation, but let's not worry about what that notation is at this moment. You know, this is representing this state, this is representing this state, and this state can be decomposed like this. Now this is what combination? This is called a linear combination. Linear combination. So now you have these coefficients here. You have these coefficients here. Now these coefficients are called probability. They are coming from probability, right? So they are called probability amplitudes. They are called probability amplitudes. Now, probability amplitudes are related to probability by what way? Probability is square of mod square of the probability amplitude. Okay, so probability is equal to mod square of the probability amplitudes. And probability amplitudes can be in general, complex, and that is why we have to take mod square, not just the square, but modulus square of this. Okay, so this is something which we require to understand. Now, why this complex coefficients are required in this particular experiment? Okay, maybe real experiments are fine, but if you do this experiment with different polarization states, you will get the same probabilities for a variety of initial polarization states. Now, to understand getting the same probability, but the state is not the same because the polarization state is different. Okay, for example, you are so for example, if you take 45-degree polarization state, let's say diagonal polarization state, that can be written as 1/√2 times horizontal plus 1/√2 times vertical. So this is how you can write it. Okay, so in the same way, if you take right circularly polarized state, that can be written as 1/√2 times horizontal plus I/√2 times vertical. So now if you look at the probability, suppose let's say that you are using this polarization state in diagonal space. What is the probability of so let's say, okay, so let me just discuss this carefully. So let's say I have a source here, and then all the photons are coming in d diagonal state, and then I have put a vertical polarizer here, So if there are n, I will get n/2. So what is the probability of transmission? Is equal to half. What is the probability of absorption? That is also equal to half. Now let's do another experiment. Source, and then I have, let's say, right circular, polarized, and do the same experiment with this one. Then also I will get n/2. So what are the probabilities? It is same, but the state is not same, right? So this is D, this is RC, but this result, probability wise, it is same, but then the state is different. So we cannot just use probabilities to differentiate the states, but then we should use square root of the probabilities. And let me tell you, quantum mechanics is the only subject in the entire physics mathematics that I know of where square root of probabilities are important. Nowhere else square root of probabilities are used. Only in quantum mechanics square root of probabilities are used, and that is required because there is a multitude of states. Even if you take, instead of RC, you take LC, left circularly polarized, you will get n/2. You can also choose a different elliptical polarized state to get n/2. So all of this can be understood only if you use square root of probabilities, and that is the reason why we must represent state with the square root of probabilities, not with the probabilities as such. Okay, so this is the reason why we have to use the state as a linear combination of different possibilities. Yes, any yeah.
Sir, here for both two different states, the outcome is same. So from the outcome, we can't distinguish the initial state, right, sir?
Yeah, from the average of this, you will not be able to tell whether what was the original state.
So, sir, this E phi, that e to the power phi in the state, cos theta, sin theta, E phi, whether that phi is measurable in experiment.
Yes, you can measure phi. Okay, so we will have to, of course, go a little beyond this one. Phi can be measured from interference. Okay, so the relative phase can be measured from the interference experiments.
Okay.
Yeah.
Okay, sir. Thanks.
Yeah. So this is the requirement for the state vector to define this way. Okay, in conventional quantum mechanics, you might have studied when you did your quantum mechanics course for the first time, there is something called a wave function, and wave function is basically probability amplitude, and probability is mod square of the wave function. Okay, so we will connect it anyway slowly, but the idea is I'm trying to motivate all this from a simple experiment, and how we came to the concept of probabilities, and how we came to the concept of state vectors. Okay, so I thought of introducing one more concept today. If there are any questions or very important questions without which you cannot understand, you can ask. Otherwise, I want to introduce within whatever short time that is there one more experiment, which will be somewhat different from this experiment, but that will also teach us a lot of quantum mechanics. Are there questions?
Sir?
Yes.
Sir, here the probability amplitude, can we somehow connect it to the actual amplitude of the wave packet? Like if we consider a photon as a wave packet, and if we consider its amplitude, can we connect it?
So the amplitude of the wave packet means, I think you are talking about a wave has an amplitude. In that sense, you are asking, right?
Yes, sir. Sir, photons, we can consider them as wave packets, right?
Correct. Yeah, you can actually. So essentially, what I'm trying to say is that if you write down a wave function, okay, how you interpret what that wave function is, nothing but it is a probability amplitude. Okay, so suppose let us say you have some kind of an envelope like this. Okay, so if you want to call this as a wave packet, okay, and this is what your psi of x, let's say. So as a function of x, this wave packet has got this kind of a variation. Now you say that at this point x, so you have psi of x, so let's say x naught. At this point x naught, let's say this is the value of the wave function. Now if you take a small region around that and call it as dx, then mod psi of x square dx is the probability. Suppose if this is the wave function of a particle, this is the probability to find the particle at so in x naught and x naught plus dx. So in this interval, so this is the probability, and this is what we call as Born rule. This is the Born interpretation, right? Max Born has interpreted this from the wave function. Okay, so this is basically the solution to your Schrodinger equation, and if you find out this wave function, the amplitude, I hope this psi of x naught is what you are calling as amplitude, if I understood correctly, and this amplitude is related to probability in the same way as mod psi square dx will be the probability at that point. This mod psi of x naught mod square is called probability density. Okay, that is the language which is used in continuous probability distributions. Okay, I hope that was the question.
Sir?
Yeah.
Sir, are there any experiments done at the lab scale using single photon source?
Professor, mistakenly I have muted you. I permitted another one. You please unmute.
Hello. So, could you hear what I said earlier?
Yes, sir.
Sir. No, sir.
No, students could not have heard, Professor.
Okay, from
last 1 minute.
Yeah. So essentially, what I'm trying to say is that So your question, the latest question is that can you do experiment in the lab with single photons? Answer is yes. All that experiment that I am discussing, okay, even though I don't know how to do it, but it can be done.
Okay.
Okay, I just want to discuss one more experiment. I don't know if we have enough time. Okay, we have 5-6 minutes. So let me just at least. So I'm going to introduce. So let us sign off with this experiment. But this experiment is very important. I want you to think about this experiment, and probably you should discuss this experiment with your friends, and whatever you have learned about this experiment, whatever doubts you have this experiment, I think it is better to discuss with your peer group, so that you will your understanding or lack of it will surface out. Now I'm going to introduce another element called a beam splitter. Okay, and usually beam splitter is kind of a semi-silvered glass plate, and we use this in optics lab. So what happens is, suppose you have a source and it is giving like electromagnetic waves, okay, and then you have a beam splitter which is represented like this, let's say beam splitter, and if you have an intensity I, then I/2 intensity will be transmitted. Okay, so this is transmitted, and then another half of the intensity will be reflected. So I/T will be the intensity that is reflected here. So this is basically what happens in a kind of a classical experiment. Okay, so now I'm going to ask the question. Suppose I have a source of photons. Okay, so let's say I'm getting these photons in this way, and then I put a beam splitter here. Okay, so now what can happen for a given photon at the beam splitter? Okay, so to understand that, let's say that we will put a detector D1 here and another detector D2 here. Okay, now let's say that we do this experiment photon by photon. So when one photon is passing through the beam splitter, what happens? That is a good question to ask, like in the previous case. Now to understand that, we have to see, suppose I send a photon number 1, then observe which one of these two detectors is clicking. Okay, if D1 is detecting that photon, D1 there will be a click. If D2 is detecting that photon, D2 there will be a click. Now exactly like in the previous case, what we observe is that for a given photon, either D1 or D2 will click. And we don't know, we will not be able to tell beforehand which one of them will click. Okay, so either D1 or D2 will click. Okay, so for a given photon, either D1 or D2 will click, and I'm not going to labor upon discussing this. I'll simply write randomly. That means we don't know which one will click, but one of them will click. So what does that mean? That means a given photon has two possibilities. What are the two possibilities? Transmission or reflection. It will be either transmitted or reflected. Okay, and if you are using n/2 n number of photons, n/2 of them on an average will come here, and n/2 of them on an average will come here. Okay, this is the observation. I mean, if you do an experiment, this is what you will observe. n/2 of them will go to D1, n/2 of them will come to D2. So now from this, what we understand from this what we can understand is that a photon, there is a probability of transmission is equal to half, and there's a probability of reflection that is also equal to half. Probability of transmission is equal to half, and probability of reflection is equal to half. Okay, so this is consistent with our observation that there is an n by 2, n by 2. Now let us just do this experiment a little, one more step further. So we are getting photons. Then I have a beam splitter here. Then this photon will actually decide randomly to pass this one. That means these photons are transmitted, or it can go this way. That means these photons are reflected. Now what I will do, instead of putting a detector here, I will put another beam splitter here. So let me call this as beam splitter 1 and this as beam splitter 2. Or I can put another beam splitter here, which is beam splitter 3. And then I can put a detector D1 here, and put a detector D2 here, and put a detector D3 here, and put a detector D4 here. Okay. Now, what can you say about, suppose if I am having n number of photons in this space, then what will be the number of photons here? N by 2. And what will be the number of photons here? This is also n by 2. This is from our previous case, right? N by 2 of them will be transmitted, n by 2 of them will be reflected. Now, how many photons will be detected at D1? How many will be detected at D2? How many will be on an average? That of course. Okay, so tell me D1, D2, D3, D4, what will be the number of photons that will be detected?
So n by 4.
Okay, so one possibility is that this is n by 4, this is n by 4, this is n by 4, this is n by 4. Is there any other possibility? Is there any other possibility?
Zero n by 2, 0 n by 2.
0 n by 2. Why? 0 n by 2, 0 n by 2. Okay, at least I will list it as another possibility, but tell me why.
Just everything goes to D1 or everything goes to D3.
Sir,
Like
n by 2, 0.
So that means there should be n by 2, 0, right?
N by 2, 0, 0
yes,
n by
sir.
2.
N by 2, 0, and n by 2, 0. Right? So what is the logic?
0 n by 2. 0 n by 2.
Okay, tell me what is the logic? Why n by 2 comes to D1?
Because previously we discussed that, like, when we introduced a slit like polarizer, it was then whatever the state, like the photons which came out of the polarizer, it remains, like if we keep another polarizer with the same orientation, we got same results.
Correct.
That means the state of the photon is remains same.
Correct. So you are expecting that. So at the beam splitter 1, this is transmitted, and hence it will be transmitted at beam splitter 2 also.
Yeah.
And so that this n by 2, okay, makes sense, and this 0 also makes sense. Now why D3 is 0?
Because similarly, like whatever reflected is there, reflected term, it will be perpendicular to. Oh, sorry.
So that means this should be n by 2.
Yeah.
Okay. So according to your logic, n by 2 0, n by 2 0 it should be. Correct?
Sir, can I make a
Yes, sir.
comment here? Like,
just 1 minute.
okay.
So let us complete this argument. So Sharath, is that clear? Is this what you are
Yes, sir.
trying to say?
Yes, sir. Yes, sir. Yes, sir.
Okay.
I thought the second split is like I thought differently. That's
Yeah,
it.
yeah, fine,
Sorry.
fine. But now it is n by 2 0, n by 2 0. Correct?
Yeah, yeah.
Okay. So this is another possibility. Now, if you ask your, I mean, if you just do your experiment, okay, if you do your experiment and then look at the results, what you get is this. Okay, you will not get this. Okay, how do we understand this? You will get n by 4, n by 4, n by 4. That means this photon is transmitted at beam splitter 1 does not mean that it will be transmitted again. Okay, so at every beam splitter, it exercises both options, either transmitted or beam splitter. Only then you can get n by 4, n by 4, n by 4. Okay, now it is a very good attempt to carry forward the understanding that you have obtained in the previous experiment to this experiment and expect this to be the result. Okay, expect n by 2 0, n by 2, n by 2 0, this to be the result. But nature is subtle and it gives you this result. That means there is a big difference between what happens for a photon at a polarizer when it crosses a polarizer to what happens to a photon when it crosses a beam splitter. And in quantum mechanics, these are two very different types of things, evolution that a system can take place. Okay, so beam splitter does not. There are two possibilities: reflection and transmission. Somehow, beam splitter does not choose one of them, whereas in the polarizer case also there are two possibilities: parallel and perpendicular. But polarizer chooses one of them. So there are certain operations where one of the possibility is chosen, and there are certain operations where possibilities are not chosen. All possibilities are kept alive. Okay, so in quantum mechanics, these are two kinds of things that happen. The situation where all the possibilities are kept alive is called unitary evolution or unitary operation. So beam splitter is an example of unitary operation. Okay, so this is an example of unitary operator. Okay. Now, what is polarizer? Polarizer actually chooses one of them. There are many possibilities. One of the possibility is chosen. Okay. So the polarizer actually is a measurement. Okay. So now you have a quantum system at time t equal to 0. As time progresses, there are two kinds of evolutions that are possible. One is called unitary evolution, which will not choose different, all possibilities are kept alive. Whereas when you use something like a polarizer, a measurement is done. A measurement will actually kill all the possibilities and only keep only one possibility alive. Whereas unitary operation will keep all possibilities alive. Okay, so these are the only two operations that we come across in quantum mechanics. Okay, so I want you to ponder around this point, and I will stop it here with this experiment, and we will in the next class make some more progress with this set of experiments. Maybe I'll introduce a few more experiments. And after we discuss a few more experiments, from the knowledge that we have gained from these experiments, we will straight away be able to formulate all the postulates of quantum mechanics. I'm stopping here if you have any questions.
Okay, sir. So the beam splitter is acting as a single qubit gate.
Yes, yes.
Okay. So there was once one like hypothesis, wrong hypothesis, that there are two kinds of photons. Like one is the transmitted type, one is reflected type.
Yes.
So some photon has R written on it, and some photon has T written on it. So
there is no such labeling that is there.
Yeah. So, but from that logic, we are getting n/2 n/2.
Correct.
Okay, sir.
Sharath, is that clear?
Sir, I was knowing, but I wanted to discuss with you like from previous experiment. Like.
Okay, very good. Very good.
So one question, I don't know if it's quantum mechanics. It's not quantum mechanics, but it is vector space. Suppose we have a DNA strand and there are adenine, guanine, thymine, cytosine, 4 nitrogen bases. So can we think that it is like a 4-dimensional vector space? Can I create a 4-dimensional vector space with the DNA strand?
See, this kind of so any modeling or writing some mathematical structure to any physical system depends on what you want to do. For example, if you want to develop a model of some kind of information theoretic model like that you want to make, then such a modeling makes sense. Okay, so most of the times modeling is based on what is that you want to discover.
Okay, so information theoretic models usually using basis 2, like Shannon entropy is created using log to the base 2.
Correct.
So, like, why the beats are favored? Like, is it just a convention?
Yeah, that's true.
And so we
because
can
our digital thing is always 0, 1. So since there are 2 possibilities, base 2 is convenient to represent it.
But if we use some time in the future, if you want to use Q treats or Q dits, then we should change that.
Yeah, that is correct. But classically, we always have bits, right?
Yes, sir. Yes, sir. But qubits we also have like base 2. But but in like Q treats or like higher dimension. So
yeah. But anyway, let's not deviate too much into that topic.
Sir, is this experiment is exactly case of Stern-Gerlach experiment?
Yeah. So whatever I'm discussing with photons and beam splitters and the polarizers, this entire thing can be also put it in. Not audible. Hello, can you hear?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So what I'm saying is that whatever I have discussed with the photons and polarizer, beam splitter, etc., we can also discuss with spin and Stern-Gerlach. Okay, that's another system where all these things can be discussed.
Okay, sir.
So what happens if we use another beam splitter, means beam joiner? Like
so that I don't have time today to discuss, but we'll consider that in the next class. So if you have some feedback on this, you can give, because I feel that compared to last class we have a lot of reduction in the strength. So do you gather that this kind of discussion is not considered not very useful by your I mean, is it the general feeling among you that is why the strength is reducing? So any of you who want to make a comment on this, or you have any feedback on this, so you can speak, or maybe write in the chat box, or give your feedback in the Telegram group, whatever. I think we had about 60-70 students last class. The absolute number of students is not a concern for me, but if that has some message for me, I would like to know. And if there is something that I can do, I would like to do.
Sir, sir, this is very nice way to introduce the subject, sir, because in most of the quantum class, in the first class itself, this vector space, all these mathematics were done. But I feel this is very interesting, sir. For me, it is very nice.
Yeah, so I also thought that we should approach it from this sense. Will be physically little motivating, and of course we have to finally do all mathematics. There is no shortcut, but we do with mathematics with a good understanding is always a pleasure to do. Otherwise, it is sometimes pain.
Yes, sir. Sir, one question, sir. This beam splitter, sir. Here, half of the photon reflects and half of the photon transmits on an average. Now, sir, can we control that? Suppose 1/4 reflect or 3/4 transmit. Do we have that control, or always this will be half?
No, I think you can control. If you ask me how to do it right now, I don't know, but I think you can control that.
That can be done.
Yeah.
But the fundamental principle of polarizer and this beam splitter is different, even though it can control.
Yes. That does not depend on this 1/2, 1/2. Okay, so that's what. So precisely what I'm trying to say is that beam splitter does not select one of the outcomes. It will keep all the outcomes alive.
Yes, sir.
Whereas polarizer will select one of them.
Yes, sir.
So keep this kind of
keywords in mind. These two. Can I add words, sir? So I think these two experiments are best experiments to show the measurement, sir. I think whatever you have done, it's very good, sir.
Yeah. That's what. So when I studied quantum mechanics, all these things, measurement, unitary evolution, they are introduced with such a mystery that it took at least 10 years for me to understand what they are. So I am trying to not to create so much of mystery, and that is why I am trying to use these kind of simple experiments.
Sir, till now also many of the students are feeling when unitary words comes, it's like you operator, you dagger, nothing physical.
Yeah.
Sir, thank you, sir. It is new way of understanding for states.
Jivanandam.
Yes, sir.
So I did not ask you. You are from which place?
Sir, Government Arts College, Udolpet, sir. Naina, sir. Student.
Very good. Okay.
So it was very unconventional, sir. Very informative and unconventional.
Okay. Yeah. So that is all nice, but I'm still a little bit uncertain about why there is a reduction in the attendance. But there can be, the answer for that maybe I don't know. And I would like to know possible answers. Okay, so if there are no questions, then we can close. Professor Yogarajan, maybe.
We may close. Students, do you have any further questions? Otherwise, we can close.
Yeah.
So I mentioned that DNA thing because I was reading about DNA computing. Like we have quantum computing related to quantum information, quantum mechanics. So where do we use the qubits and stuff? But in parallel computing, another stream is DNA computing. So I don't know much about it. So there, can we use 4-dimensional vector space or something like that?
Yes, I think it is a definitely a possibility, but I also don't know much about DNA computing.
Yes, sir. Yes, sir. Like also you can use like a protein like 20 amino acids, so you can use 20-dimensional vector space.
Yes, in fact, see this artificial neural network and these things, they completely based on vector spaces only. So you define vectors and you training set, etc., etc. Everything is a vector space concepts. All these linear algebra concepts are very much used in what is called artificial neural networks and
so evolution of the neural networks.
Yeah.
Yes.
Yeah. Okay. So then.
So excuse me, sir. One more question, sir.
Yeah.
So this beam splitter experiment, we can do it really in lab. I'm asking this because if anything is interacting with the system eventually suddenly collapses, right? So that it's like a measurement process.
Yeah. But it's
Here
not like
it's not a measurement.
It's not a measurement. That's what I'm saying. So beam splitters actually they so if you want to understand it like this, let's say you have a state vector. So beam splitter actually rotates that vector. Okay. So whereas a measurement will actually, as you said, collapses that vector. It will actually choose one of the things. So beam splitter will simply rotate that vector. Let's say if the vector is like this, it will rotate it. This is just a visual thing I am saying. Okay. So the rotation is not in a physical space. It is in a Hilbert space. So that rotation is not to be understood like a physical rotation, but it's basically a transformation of one vector into another vector. That is what it does. So it does not choose. Whereas measurement, what it will do, it will project that vector. Suppose you have a vector, you have a vector like X. Go ahead.
So it's like a change of basis, right?
Which is like a change of basis?
Beam splitter.
Beam splitter is not like a change of basis. Can be a unitary transformation, but unitary transformation of a vector is simply rotating that vector. Okay. Whereas measurement is going to project it. Suppose you have a vector in xy plane, you project it along the x-axis, then only you will get only x values, right? Y is completely lost. So measurement is a projection, whereas unitary operation is just a rotation.
Okay.
So you can be written as a combination of rotation matrices.
Yes, you can write.
And like a combination of then Pauli spin matrices, the rotation matrix, the exponentiation of Pauli spin matrices.
Correct.
Okay, sir.
How these two things, polarizer and beam splitter, can you put in operator language? How we can?
We can write down the beam splitter as an operator, but we cannot write polarizer, because polarizer is an apparatus, right? So you can do some kind of a post-mortem or post facto analysis of writing a projection operator, but that is after knowing the result. For a polarizer, I have this operator, like that we will not be able to write.
Okay.
For that matter, for any instrument, such a description is not possible.
So measurement is like taking an inner product, no sir. So we can use that inner product and then mod square. So we'll get the probability.
You will get the probability, but that is not the measurement per se. That is, you are going to interpret after getting the result, how probable that result is, that you will get by taking that operation.
So we can use projection operators, no sir?
Projection operator you can use, but projection operator is also like a posteriori description. That means you finish the experiment, see the result, and then tell, this is what has happened.
Yes, sir. And so there is something called POVM. Like I was reading, like I didn't study it properly.
So POVM is one language where this can be a little bit enriched. That is, this projection operator thing can be enriched, but that is also a posteriori only.
Okay, sir. Thank you, sir.
Yes.
Sir, in beam splitter, the probability is independent. For example, for transmission and for reflection, it is half and half. Whereas in the polarizer, it depends on the angle.
Yeah, that's what, just like, okay, you ask your question.
Yes, sir. So it depends on the angle. So when we take a measurement, we fix the angle. So that is the reason we get only one possibility. Whereas in beam splitter, we don't have any option. Like the probability is independent.
Okay. So this is, this difference what you observed is an incidental difference only. See, for example, in polarizer case also, when I take diagonal and vertical horizontal cases, I will get a half only, right?
Yes, sir.
But that does not mean that if I get, if I use a vertical polarizer and if I use another vertical polarizer, I will get 100%. That means this a diagonal has a combination of vertical and horizontal, but a vertical polarizer, when it passes through, probability is half, but what comes out is a vertically polarized light, photon only, correct? So among vertical and horizontal, it has selected vertical and killed horizontal, correct?
Yes, sir. Yes.
So, but here among reflected transmitted, it did not kill anything. It is keeping both properties alive.
Okay, sir.
Okay, so then we can. George,
Shall we close?
Yeah, you can close, Professor Yogaraj.
Thank you, sir.
Okay.
Thank you, Professor.
Thank you, sir.
Yeah. Okay.
Thank you, sir.
Good night, everybody.
Good night, sir. Thank you, sir.
Good night, sir.